afternoon, everyone. This is Mike Dietz from the Center for Land Use Education for Research at UConn. And I'd like to welcome everybody to our webinar today about road salt use in Connecticut. And just briefly to introduce myself, I'm a water resources educator here at UConn. And Lucas McNaboe will be co-presenting with me today. He's a master's student in the Department of Natural Resources and the Environment at the University of Connecticut. So just very briefly, a little bit of introduction here before we get into the webinar. So this is the second webinar in our 2017 series. The first one is available in our webinar library if you'd like to check that out, about our MS4 program. And we will have others coming out as well that you can see on the listing there. Okay, just a last slide about a little propaganda about CLEAR. So we pull faculty members from 3 different departments at the University of Connecticut in the College of Ag, Health and Natural Resources and the Connecticut Sea Grant program. We have a variety of programs that started with the Connecticut NEMO program, or Non-Point Education for Municipal Officials. We also expanded to a national NEMO network. We now have a formal geospatial training program, a land use academy, and an extension forestry program. And everything is really tied together under this umbrella of providing information, education, and assistance to land use decision makers in support of balancing growth and natural resource protection. So land use decision makers might be municipalities. That's how we started out with the NEMO program. Or it might be just an individual citizen of the state who's managing their own piece of land in their backyard. Okay, so on to our topic at hand today. So this is a good time of year to be talking about this, coming out of a nice winter storm where everybody was faced with trying to drive on our roads and wanting to be able to do that in a safe manner. So sodium chloride is what we're going to be talking mostly about today. And sodium chloride, just very briefly, is an ionic bond, and I'm not trying to give anyone some bad flashbacks of chemistry classes in high school or college. I know these things can happen, but I just wanted to introduce the topic today and point out the fact that the sodium and chloride ions do dissociate in water, and that becomes very important because chloride is a highly mobile ion, a negatively charged ion that moves through soil very easily because soil particles have negative charges as well for the most part. So it tends to be repelled and move conservatively through soil, which is what causes so many problems. So on a national level, if we look at how much road salt is being applied to our landscape from the 1940s when these data were first collected, we can see that it started out very, very low and has climbed up to over 30 million metric tons of road salt being applied to our roadways in most recent years, around 2015. We can also see with so the black squares represent that mass of road salt applied. The red circles represent the percentage of road salt or the percentage of total use that road salt represents. So that has also increased from fairly low back in the 40s through the 80s up to almost 50% now of salt use being just used on roads. If we look at some regional work on water quality, so in surface waters, this is a study that's referenced in some work by Kaushal and some other researchers. And I'm going to be highlighting quite a few studies today throughout the webinar. I do have a list at the end of the presentation that has links off to all these works. And I'm going to talk with Dave Dixon, our resident IT guy, guru here at CLEAR, who helps us with all such problems. To make sure that we can actually have you access those links at the end of this webinar, because typically I think with the webinar recording you won't be able to click on those links, but we'll make sure to post something so that you'll be able to access those links because there's some really valuable studies there. So on to this study here. So this is up in the White Mountains that Kaushal references. He also talks about several other studies across the country that look at this increase over time. So this one starting back in the 1960s along our bottom axis here. This is time. And we have chloride concentrations increasing. You can see when they constructed the interstate highway, this was Route 93 up in New Hampshire. And we have this gradual increase and now a steady climb in our chloride concentrations in the surface waters nearby that highway. Whereas the reference stream that they talk about in the Hubbard Brook experimental watershed remains right around less than 5 to 10 milligrams per liter. So this is a classic example of our surface waters gradually increasing over time as a result of road salt. Here's another key piece of work that I've looked at and referred many people to. This is a great job that John Mullaney from our Connecticut, from our Connecticut USGS office did with some colleagues of his, looking at a variety of aquifers in the northern regions of the country, so where deicing occurs. So the link is here, but again, that will be available for you at the end, the full reference. And this is just a little summary from their study, from that USGS work. So I'm going to key you in on the right-hand side of the screen here. If you're not familiar with a box plot, this is a very simple way of presenting data. So the box represents the bounds of the 25th percentile of that data on the bottom and the 75th percentile on the top. And what that horizontal line across the middle represents is the median of that data. So if we look over here, let's say at our forested landscapes, so again, this is chloride concentrations in milligrams per liter in our groundwater. The median is somewhere around probably 4 to 5 milligrams per liter. If we look at our urban areas, sorry, clicking too fast there, our urban areas, we can see that that median is probably between 50 and 60 milligrams per liter. So a striking difference in for our different land uses impacting the concentration of chloride in the groundwater in those areas. What this dashed line is here is the secondary maximum contaminant level for chloride. So chloride, I'll talk about this more in a little bit. Chloride does not have a primary drinking water standard. It's not toxic to humans in most concentrations that we would see, but it does have a secondary maximum contaminant level that is in place to protect corrosivity of pipes and other water systems, and also for those related to sodium that might be on a sodium-restricted diet. So we'll talk about both of those in a second. So on to surface waters now. So again, we have our forested watersheds here, fairly low median, maybe 20 milligrams per liter. And again, I will key you in on the urban here, and we note that the median chloride concentration in surface waters in our northern regions of the country, as reported by USGS, is right around the chronic criterion for aquatic life, around 230 milligrams per liter. So that really means that at least half of the samples that they found were above that chronic criterion for aquatic life. So half were below, but half were above. So that's quite a concern for the health of our aquatic species. And let's not forget sodium, although chloride is what we're mostly talking about here because that's the most mobile. Sodium, we see a similar pattern. So forested, the lowest levels, agricultural watersheds, a little bit more. And then in our urban watersheds, again, our median concentration is above the drinking water advisory, so even more than half, as you can see here, of samples were above the drinking water advisory of 20 milligrams per liter for sodium for drinking water systems. And just briefly, it's not just in the United States, so same researcher, Kaushal, doing some different work, summarizing a little bit of study from other regions. So in Europe, in Japan, similar increases in our surface waters of chloride climbing up over time gradually. And back to Connecticut, we have some great work here that was done by Gary Robbins and James Casanelli, his master's student. So Gary Robbins is our groundwater expert in the Department of Natural Resources Management, Department of Natural Resources and the Environment at UConn, and did this statewide study looking at data all the way back from the late 1800s till current time. And this shows, on average, across the entire state of Connecticut, how groundwater concentrations have changed from the late 1800s all the way through early 2000s. So this is an average concentration now, so 20 milligrams per liter of chloride, not super concerning. The trend is concerning, but what is documented in the research by James and by Gary is that there are quite a few localized areas where these concentrations are much, much higher. So this general average trend may not be too alarming, but when you look at some of the localized data, it can be more concerning. So we do have a quick question that I will comment on here. So the question is, Connecticut regulations for private wells and public water supplies do have a water supplies do have an enforceable maximum contaminant level of 250 milligrams per liter. That is correct, but it's a secondary maximum contaminant level It is enforceable, but it's not a maximum a primary drinking water standard where there is a human health concern for that level. But thank you again for that comment. It is on record as a drinking water standard. Okay, I'd like to move briefly into a really nice report that was published in 2015 by the Connecticut Academy of Science and Engineering. So this was entitled Winter Highway Maintenance Operations in Connecticut, and this covers a lot of aspects of winter de-icing history, trends, impacts, and actions in Connecticut. This is available on the Connecticut DOT website. The full link is at the end of this talk, as I already mentioned. So these are the authors on there: Jim Mahoney at the Connecticut Transportation Institute at the University of Connecticut, and several others from UConn as well. So just a little bit of background here, as highlighted in the case report. So prior to 2006, so if you've been here in Connecticut for a while, you are pretty well aware of this trend. Prior to 2006, de-icing in the state really was done with a sand-salt blend. So this was reactive de-icing, where snow was plowed during the storm, a sand-salt mix was put down close to the ends to provide traction and to melt ice and prevent it from refreezing. So they changed the policy in 2006 to an anti-icing policy. So they wanted to phase out road sand for a number of reasons. First of all, road sand has been found to be very damaging for aquatic ecosystems as it gets into our small streams and other waterways. And there's a huge labor cost for cleaning up all that sand in the spring. And so for those reasons, they switched to an anti-icing policy where they began pre-treating with a sodium chloride brine. So the picture on the right that you see, these pretty familiar lines that you'll notice on the highway when we have the threat of a storm coming. So this is a liquid sodium chloride brine that gets applied to the roadway. And the thinking with this is that this prevents the snow and ice from adhering to that highway in the first place. So it becomes easier to push the snow off of it when it does accumulate on there, and we'll have less slippery conditions. So also with that anti-icing policy, there was a pre-wetting of rock salt that began in that time. And the purpose of that was to prevent more scatter of the salt off the roadways as it hit. The pre-wetting was designed to help it stick to the road better and minimize what was lost off the roadside. So this pre-wetting was typically done with a calcium chloride or a magnesium chloride liquid. So from 2014 on, the policy is pretty much the same, except they've gotten away from the calcium chloride, and at least Connecticut DOT is primarily using liquid magnesium chloride as their pre-wetting agent. So again, this figured right out of the case report. So what we have here on the left-hand side are the blue bars from 1999 through 2006. These are number of crashes per winter season. So we can see the trends that it's actually a kind of a downward trend here that you'll notice. And they attribute this to other safety factors, so better vehicle equipment. So we've got more anti-lock brakes, we've got four-wheel drive, we've got all-wheel drive vehicles on the road. There was a general downward trend in our vehicle crashes during this period anyway. So if this trend if you carry out that trend through the recent years when anti-icing was taking place, the blue dashed lines here are what that would represent. So if we look at the anti-icing strategy now, the crashes here are represented in the yellow bars. The red line represents that trend. So that trend is quite a bit downward from where the de-icing trend would have led us to believe we would be. So we'd like to say that this anti-icing strategy has helped to prevent crashes on our roads and made things safer, made winter travel more safe on our roads during storms. So there were some data that were presented in the case report about annual snowfall totals in relation to how much chloride was applied. So I took some of those numbers out of the table that were in the case report and just graphed them here. So what we have, the blue dots and the blue line represent the de-icing years. So what this is the summary of the annual total snowfall. So this was probably 18 inches here in our low one, and that represented about 35 to 40,000 tons of chlorides applied. If we plot all those values and then put a regression line through the middle, that's what it looks like. Now, if we look at the anti-icing years from 2006 on, with our yellow dots and orange dots and orange line, we can see that trend line is a fair amount higher than the de-icing years. And if we look at the average of this trend, it's about 25% higher. So for our anti-icing, the takeaway message here is much less sand is being applied to the landscape. DOT applies no sand at this point in time, which is a very positive thing for our aquatic ecosystems and for maintenance costs in the state. But we do see a 25% increase in the amount of salt that's applied now with our anti-icing strategies. I'd like to just do a quick poll to make sure everybody's still with us and just get a little bit of information from you. If you have some information about when the de-icing practices in your town, so we're just going to launch it there. So if you can click any of these that apply, and if you don't know what it is in your town, you don't have to answer, that's okay. So it looks like out of those who responded, about 40% say that their town uses a sand-salt mix, 28% pre-treat with a salt brine, 38% pre-treat with a solid salt, 17% pre-wet with a solid salt, and 6% use other materials. So this is actually fairly consistent with the data that CASE came up with in 2015. Their survey was actually in 2014, but in their survey of municipal DPWs, they found around 50% of municipalities are still using sand. So you guys said 40%, so not too far off of that. But not surprising given that 2 years have gone by and I think more municipalities are moving away from sand. So I'm not surprised to see that number a little bit lower. Sodium chloride or treated sodium chloride is the primary solid deicer according to CASE. They say 13% of municipalities pre-treat with liquid. Your survey results indicate 28% pre-treat with a salt brine. So again, not a surprise to see that that's bumped up in 2 years since the last survey. And lastly, on the PowerPoint slide here now, 56% of municipalities report pre-treating with solid deicers, and you guys say that 38% pre-treat with a solid salt. So that's down a little bit from what CASE reported. So that's not exactly what I would have expected, but that's okay. Okay, so just a couple other things here from the CASE report. Connecticut DOT, along with many municipalities, are using a lot of technological innovations and driver training to optimize road salt applications. I'm not going to go into these. I just wanted to make you aware of them. These are things, the photo on the right, or there's a road temperature sensors that they use, and driver training programs are documented in there as well. I was asked before this webinar if I could look at some of the economics of this implementation to try to help municipalities make decisions. That's really beyond the scope of what I could do for this webinar, but we will consider looking at that with some of our friends at the Tech Transfer Institute here at the university to try to get that out to municipalities. But we do recognize that the economics of that is an important consideration for any of you municipalities. So just wrapping up on the CASE information. So in the CASE report, they summarized the municipal and Connecticut DOT applications of road salt. So this is tons of road salt applied in these winter seasons here across to the right. So in 2013, 710,000 tons applied. They reference a New Hampshire study that showed that municipal and state road salt loads were only about 50%, like just over half of the total. So there's a lot more salt being applied to our landscape on our private parking lots, roadways, and also other private lands. So I just multiplied that out and to estimate what the total road salt application is in our state. So these all of a sudden become staggering numbers, over 1 million tons in some years of road salt being applied to all of our roads. This is municipal, state, and private roads and private residences in the state. It's a lot of salt being applied to our landscape. So just wanted to have those numbers so you can see the magnitude of what we're dealing with here statewide. We're often asked about alternative deicers. There are a bunch of products that are listed in the CASE report. Alternative products such as beet juice and molasses. These are typically used as wetting agents on salts. They don't really, there's no product that will really melt ice like salt does and be able to be applied in a safe manner and an economic manner on a large scale basis like we need it to be. So these alternative products are helpful and they can help reduce our applications. And there are a variety of proprietary products. This magic salt is one that I've seen referenced. This happens to be the one that UConn uses. I'm not endorsing this. I'm just showing you here as an example of a proprietary product. But again, sodium chloride is really the most cost-effective chemical deicer available right now. So just like to switch now into some of our implications. So again, neither sodium nor chloride are listed in drinking water standards for human health concerns, but they are listed as was commented on. So sodium, the recommended level is 20 milligrams per liter on a national basis. Notification level is 28 milligrams per liter in Connecticut. The chloride secondary maximum contaminant level, maximum concentration, is 250 milligrams per liter. And if we look at our aquatic life criteria in Connecticut, it's 230 milligrams per liter for chloride on a chronic level and 860 milligrams per liter for acute. So that will come into play in just a few seconds here. Just to have a little bit of information here from Connecticut DPH. I had Eric McPhee from DPH give a talk at a salt conference we held at UConn a couple of years ago. And this is some information from his talk in 2014, where he showed that approximately 1,100 of the 2,500 public water systems are required to test for sodium and chloride. And as of the time of that presentation, about 3.5% had exceeded the 28 milligrams per liter in the last 5 years, and about 4% had exceeded the chloride MCL in the last 5 years. So these are fairly low percentages, which is encouraging to me. But the one thing to note is where there's a violation, they tend to be really high levels, and it makes the water pretty much undrinkable. So this is something that we're looking at with some current studies that we'll be talking about in the near future. And one other thing to note here, if you do have public water, any sort of public water system, you do have access to the water testing that is required by law, and you can request that report from your water provider. So there are ecological and biological impacts of this salt in the environment. So again, as I noted, chlorides from all sources are highly mobile in water and in soil. You've probably seen some of the damage to vegetation along the roadsides. This is from the immediate washing of road salts that spray off of the highways onto the plants themselves, the needle burn and leaf burn. But there are other longer-term impacts on this vegetation due to the high salt in the groundwater itself. So we'll be talking a little more about that. And again, on the last bullet here, Kaushal has documented and shown some other research that where plant communities in wetlands and riparian areas have been adversely affected by this increased level of chloride and sodium in the groundwater. On the ecological side, negative effects on amphibians in salt-affected systems have been noted. So some research showing impacts to breeding behavior in frogs, although some populations seem to be adapting to moderately salty conditions on the roadsides and still reproducing, but there is noted effect on their breeding behavior and also other negative impacts. And other studies, again, Kaushal notes other studies impacting fish and other macroinvertebrate populations. And this is a really important point here that he mentions in this paper, and this is the idea of chloride making its way through the groundwater and through the shallow groundwater system. It takes some time for this chloride to work its way through and come out in the base flow of the streams in the area. And what we're finding is, and what Kaushal has noted in this part of the country, is that we're seeing these high levels of chloride come out in the base flow in the summer months when the water levels are low and when the aquatic populations are already stressed because of higher temperatures and again, that lower water level. So this is just an added stress in that difficult time of year for the aquatic life. So this is a big concern. So I'd like to talk a little bit about some of the data we've collected at Eagleville Brook. So I've worked with Jack Clausen in the Department of Natural Resources and the Environment at UConn. We have a 7-year record of discharge at our Eagleville Brook station and 6 years of connectivity data that we've documented. And you can look at the real-time data on the link here if you'd like. I'm not going to go to it now just in the interest of time. But if we look back to 2011, when I started measuring conductivity at that site, so again, this is a little different from chloride now. This is conductivity. This is a measure of all salts in the groundwater, or sorry, in the surface water. It's the ability of that water to conduct electricity. The units are typically microsiemens per centimeter. And in our other research at UConn that Luke will be talking about, we found that chloride is about 1/3 of the conductivity. So that'll come into play in just a second. But what I want to point out here is it's hard to see these low concentrations in the non-winter months. But you can see these peaks through the whole winter season. There's 11 to 12, there's 12 to 13, 13 to 14, 14 to 15, last winter 15 to 16, and I don't have this winter's data available yet. But these huge spikes in the conductivity during the winter months are very obvious in Eagleville Brook. These are concentrations of seawater and certainly of brackish water for a large portion of the time, but seawater for very short periods of time during those runoff events. Now what I'd like to show you here, this is that same data, but what I've done is just capped off the left-hand axis here at 5,000 microsiemens per centimeter so that we can see these low levels. This is what I'd like to point out here. So what this is our base flow concentration. And what I want to point out here is back in 2011 when I started monitoring here, we were just under 1,000 microsiemens per centimeter in our base flow of conductivity. And this has climbed, and this line represents how base flow has increased to our most recent season here of over 2,500. So it's gone up 2.5 times, or 250 or 250% since 2011. And I have this line at the top of the base flow values here, not the bottom, because this is the true base flow at the top of here. These low values are what happens when a rainfall event comes through. We get a flush through of rainwater which has very low conductivity, and it drops it very low in the stream. And then it always comes back up to this constant level, which is what we consider our base flow. So if we look at our chronic aquatic life criteria that I mentioned before of 230 milligrams per liter, if I assume that our chloride is about 1/3 of conductivity, it's here. So we can see that most of our base flow is now above that chronic level. And if we look at our acute aquatic life criteria, it's around 2,500 microsiemens per centimeter. And most of our winter big events are above that level as well. And now we're starting to get up to the point where our base flow is right at that acute level as well, which is a huge concern for aquatic life in that stream. So now I'm going to turn it over to Luke to talk about some research that we've been doing on campus.
Hello everybody. As Mike just said, we're going to talk a little bit about the research that's going on. We're investigating the salt levels in the groundwater that are occurring right now. We started this research in October 2014, and we'd be remiss to not include our collaborator Gary Robbins in the Department of Natural Resources at UConn as well. So in the fall of 2014, we installed 3 groundwater wells on the Storrs campus, and then last fall in 2015, we installed 5 more. In each of those wells, we set up a little sensor that can measure the water level and the conductivity, and those collect a reading every 10 minutes. So that gives us a really good continuous measurement of the groundwater chemistry. So for those of you familiar with the UConn campus, our area is circled in red there, and you can also see Swan Lake at the top, chemistry building. Here's the student health center, and this is the nursing building, Storrs Hall, this parking lot right out front of Storrs Hall. So this parking lot, even though it's a permeable asphalt, it still gets the similar salt treatment to the conventional pavements. And this isn't really necessary because when the meltwater falls on this parking lot, it typically percolates right through, so you actually you only need a fraction of the salt applied to that. Regardless, it gets the same treatment for logistics, I imagine. Okay, so here's a diagram of our lot here. We have a well, we have a sensor in each of those wells. And the 3 at the bottom here were the ones installed first, and then later on, last year we installed these up top. Just real quick, this is a graph that shows the conductivity measurements that the sensors make on the x-axis and the chloride level that we're interested in on the y-axis. So we took a couple samples from the ground. We're at like 70 samples now, and made this relationship to establish that it's about 1/3 of the conductivity is the chloride. Okay, so what we're looking at here is that same diagram that we saw earlier, now with the water table elevation shown in blue. So what happens is water flows from the higher elevations in darker blue up here, downstream, down gradient, to the lower elevations in lighter blue there. So that generally follows a north-northwest direction here. So before we go into this, so today we're going to bring out some chloride data from these 3 wells, starting upstream here, and then moving a little bit further downstream, and then finally the furthest down gradient well here, DG3. So starting up top at UG1, we're seeing this graph which shows the chloride concentration over time. This is 2 years of data coming up on 3 years of data. Okay, so over here in November 2014 we installed it, and we found about 1,000 milligrams per liter in the groundwater. This was a little bit higher than expected, and we'll get into that a little bit later on. So the well responded pretty quickly once salting started around December 2014, and it reached more or less 3,000 milligrams per liter throughout the winter. Just before the probe stopped measuring in the summer of 2015, we also saw this spike right here, and that's attributed to a huge flush of chloride coming in that was locked above a frost layer. So when that frost thawed out, a lot of the chloride that was trapped in the first couple inches of soil had a chance to percolate down to the water table. We assume that during this gap of data, the rainwater helped dilute the chloride level in the ground all the way down to where we see it here, because that's what happened in the next summer. And the minimum level of chloride that we found was about 1,200 parts per million. In context, as Mike said, 250 milligrams per liter is way down here. That's the secondary water quality standard, and 20,000 milligrams per liter is about the salinity of seawater. In any case, so minimum of about 1,200, and then again we see a pretty quick response once salting begins, and then it sort of dilutes through the summer, coming back down to the baseline of 1,000, 1,200. This is just this winter starting to increase from the most recent salting events. All right, moving downstream. On the other side of the parking lot, right down gradient from there, downstream from there, we see this well, down gradient 1. This is drilled in sand, and we'll see that water has a chance to flow through that much quicker in a second. Okay, so this is what I was talking about with the water being able to flow very quickly. So right off the bat, it's similar to what we just saw. We have chloride over time, and each winter there's a characteristic pulse of salt moving through. Now what's interesting is that when we first installed this well, the chloride was effectively below the detection limit. And so what that tells us is that rainwater that is able to percolate through the permeable pavement can dilute that 1,000 milligrams per liter that we saw further up gradient. In any case, it responds very quickly to each storm event once the winter begins. You can see these are pulses of salt that gets through on warmer days following salt applications. So the peak in the 2015 winter was around 6,000, and then it increases. Last winter we saw almost 16,000, and this winter we're exceeding the salinity of seawater. Of course, this gets diluted after salting ceases in the winter time, but the question remains: where does this salt go? So then we'll look further downhill at the third well today. This is about 200 feet away from the parking lot, located in a very thick glacial till through which water moves very, very slowly. So this well, as I mentioned, we started monitoring this one in 2015. And what we see, which is kind of interesting with this well, is that the peak salt level occurs right around New Year's, and the minimum, of course, is over here in July. But why would the peak... Oh, we have a question right here. about how deep the wells are. These are shallow aquifers or shallow monitoring wells, not going more than 17 feet deep. Sorry, that was just a quick question that we got from a listener. In any case, this well reaches peak chloride in around January, December, and then starts to decrease throughout the salting period, and then increase again in September, August. And our calculations show that this lag in the peak takes about 10 months, and that matches up pretty well with the lower permeability of the soil in that area. Oh, one more thing before we move on to the next slide. This minimum here is about 1,000 parts per million, and we can, or milligrams per liter, and we can assume that that discharges directly into the Swan Lake, which is a little bit further north, which is a little bit further down gradient. So one of the implications that I'll mention because of this is that high sodium chloride in the groundwater will increase the mobility of metals that may have already existed on the soil. So here we have sodium in the green, we have calcium in the red here, and we have magnesium in the blue. And what the main takeaway here is that when you increase the sodium, all the other ions that were typically stuck onto the soil particles have a chance to get knocked off of the soil and into the groundwater solution. So this increases the hardness of the water. And what else did I want to say about this? The water hardness increase is a concern for anybody who has appliances that might get corroded over. I think that's all I wanted to say about this slide. So one of the big reasons why we're seeing the high background levels, about the 1,000 parts per million milligrams per liter chloride in the furthest well Upgradient, is that there's a lot of sidewalks in that Upgradient watershed, and these get heavily salted because of high pedestrian traffic and understandable safety concerns. And after they're applied to the sidewalks, they dissolve and percolate down to the water table. And if you look at this map of, or this Google image of UConn, you can see the extent of sidewalks all across the campus. So just to summarize the main takeaways from this, what we're seeing is that even though salting occurs seasonally, this urban aquifer is going to be salty throughout the course of the year, which serves as a perennial input of salinity to water bodies like Eagleville Brook, which Mike mentioned earlier. Another big takeaway is that even though salt gets through the porous pavement in the wintertime, rainfall during non-winter months helps dilute the background chloride levels for most of the year. And these findings are consistent with other research across the country. As Mike mentioned, there'll be links at the end of the presentation. You can check those out later on.
Okay, so this is Mike again, looking a little bit bigger picture again at this now to wrap things up. So what can we do? You know, this is the question that we always get asked. It's in the foreseeable future, I don't think that we're going to see anything that's going to be easily applied and reasonably economically efficient as chlorides. So they're going to be continued to be used, into the near future. It's not practical to remove it from groundwaters or surface waters. There are methods to do this, but it's really expensive and not practical for most situations. So really the only thing we're left with right now, unless something changes technologically, is to reduce the applications in the watershed. So as I mentioned from the case report, DOT and other municipalities are trying to do this, to use technologies and driver training to reduce salt. You know, it's in their advantage, or to their advantage, to use less salt. It costs less money, You know, it's less wear and tear on vehicles. It's, you know, the corrosion issues. So less salt applied in general is a better thing, you know, for all involved, as long as public safety is protected. So, you know, it's trying to find that balance between making sure that you've got sufficient public safety while not putting on so much salt that it's causing problems for aquatic life and other things downstream. So another report here that was mentioned in the case report, and something that we've been made aware of from others, New Hampshire has set up a salt applicator certification program. So they have these very straightforward goals. First, to improve efficiency in salt use, such that the least amount of salt is used to ensure safe conditions. Number two, to reduce the amount of salt used by commercial applicators over time while maintaining safe conditions for pedestrians and vehicles. And to establish a voluntary system to track salt use. So there's a really nice webpage that has all the information about this program, and anything else you might like to read. You know, there's the full link on the bottom, but the top hot link will work as well. And one of the keys to this is that the owners who hire a salt applicator who's been certified by Department of Environmental Services are granted liability protection against damages arising from snow and ice conditions. So that's a big deal, and I think that's the key linchpin for this whole program to work, is to have that liability covered so that people aren't putting on 2, 3, 4 times the amount of salt needed just to be sure that they're covering themselves so that they're you know, less vulnerable to lawsuits. The other benefit of this program is, as I mentioned, applicators are requested to report how much salt they're applying. So that gives the state a nice way to keep track of what's being applied to the roadways and hopefully document that that's decreasing over time. So in conclusion here, for the overall webinar, deicing salt use continues to increase along with chloride concentrations in surface and groundwaters. Our Connecticut DOT is using numerous best management practices to minimize salt application rates while providing for public safety. And this is, you know, clearly evident in the fact that fewer accidents are occurring. From the UConn study, sidewalk deicing is a potentially large source of salt loading to shallow groundwater. So that's something that we really didn't expect. Those high concentrations in that Upgradient well were quite surprising to us, and have led us to do some further investigations on campus. More conclusions: there's really no other cost-effective salt alternative at this point. And as we just covered, application reductions are the only way to effectively reduce the loading to the environment. There are technological tools, sensors, things that adjust the salt application for the speed of the vehicle. You know, this is all technological stuff that DOT has used, other municipalities as well. Education is a really big factor, though, making sure an applicator, the guy who's driving the truck, knows how to calibrate that equipment and run it properly. And there's programs like the one in New Hampshire are showing great promise in helping applicators reduce applications and hopefully showing long-term decreases over time. One last conclusion here, I would say that if you do have a shallow well and you live in a developed area or near a road, I would recommend that you get your water tested. Based on our findings here, the shallow water is definitely vulnerable, more vulnerable than deep bedrock wells to chloride contamination, although the bedrock wells aren't immune either. But a shallow well is particularly vulnerable. And if you've lived in your house for a while and haven't had it tested, I would recommend doing that. And Connecticut Department of Public Health has a list of labs that are certified to do this kind of testing. Here are the references that I mentioned. So these are all live links. If you can't get some of those journal articles, if you're interested in them, please just email me. I'd be happy to send you PDFs if you don't have access. We have the nice benefit of having lots of access at the university. So happy to email stuff that anyone might need. And I will leave you here with a picture of me doing my best to reduce the salt application on the road and put it into other more productive areas. And we will check out a few questions that we have here now. So I think I will send this one to Luke about the project at UConn. So how does the increasing sodium chloride affect iron and manganese? Luke, what are your thoughts on that?
Well, we did have one sampling round for iron and manganese, and we found that they correlated pretty strongly with the chloride distribution as well. But since there was only that one sampling round in 2016, it's hard to say about how changes in chloride might might change the iron and manganese, at least at this site. But definitely, according to other research out there, their mobility could be increased.
Okay. Another question, it's too late for preventative measures in many towns. What can we do once public wells are contaminated? That's a tough one. You know, if you're consistently having levels that are above the MCLs for either sodium or chloride, there's not much you can do besides trying to reduce what goes on to hopefully bring it down in the future, and also do some sort of drinking water treatment. Or, you know, like I know, for example, of a couple of schools that had concentrations that were too high to drink. They had to switch to bottled water for drinking. You can still use the water for other things, but you know, for drinking purposes, it's recommended to keep it below that level. So bottled water is really the way to go, or to use some sort of treatment system like reverse osmosis. But you're getting into some costly changes now, which might be beyond the reach of most residential homeowners. This is from Papazaki at DPH. She says that they're finding effects in deep wells too. So again, I would agree with that our deep bedrock wells are vulnerable. And so it's probably not a bad idea if you've lived in your house for 15, 20 years and you haven't had the water tested since you moved in, and you know, even if you've got a deep well, why not get it tested? It'll cost you about $100 to get that test done. And it's a good thing to do for your peace of mind. You know, this is something that you drink every day, and it's you know, it's something you want to be aware of. So I think that's, do we have any other questions here? Oh, I've got a couple more. So do home filters work? One question. So I guess the best, there's really no filter for chloride or for sodium. The system that would be the most appropriate would most likely be a reverse osmosis. And I'm pretty sure that that's the only thing that would work. So they do work quite well, but again, they're not cheap to install.
Just want to build a desalination plant.
Right. So another question, are the DOT best management practices posted somewhere? And yes, those are available in the case report that I mentioned there. And that's available on the DOT website. Oh, was there something else down here? Okay, I'll come back to it. Also, this is from Vic Benny, says they're also finding that low pH levels pick up the metals from the pavement or soil as well. Do you come across that in any of your literature work? Luke is in the midst of preparing his thesis, so he's probably the most well-versed. So with low pH, and I think I remember that, low pH putting metals into solution.
Yep.
You agree with that?
I agree with that, and also low pH levels could indicate more fresh groundwater closer to the surface.
Okay, one more question. Have there been any studies on how far sodium chloride concentrations will travel in groundwater? This will be helpful in siting new wells a certain number of feet from roads where salt applications occur. So the chloride is definitely one that will travel further in groundwater. I believe some of those references that I've talked about do indicate some distances from roadways. So I don't have something on the tip of my tongue, but I will see if I can dig up in where I saw that in there. But I do remember reading that and preparing for this, so that information should be at least available in one manner or another. What do you say, Dave? Statewide study?
Did you just mention it? Your upcoming broader study?
That's on the radionuclide stuff. That's different. Okay. Okay. Another question is magnesium chloride worse than sodium chloride, or it doesn't matter? So as far as chloride is concerned, chloride is chloride. So magnesium chloride will dissociate in water, and that chloride ion will still move with the groundwater. So really, as far as from a chloride perspective, it doesn't matter.
2 chlorides in magnesium.
Luke says there's 2 chlorides in magnesium chloride. So you got even more for each ion of salt. So thank you. I'm glad somebody's more well-versed in the chemistry of it than I am, because that scream Homer Simpson at the beginning was for me. Let's see. Okay, I think we've got, yeah, thanks Vic. He said he hopes none of the salt from the rim of my drink got washed down the drain. Don't worry, I didn't let any of it go to waste. And that was a real margarita, believe it or not. Okay, I think we've got most all the questions. And okay, that looks like it. So again, this will be posted. I will work with Dave to get at least a PowerPoint with those live links posted as well alongside of it so that they are available. But I'd like to thank you for your attention today, and please feel free to let me know if you have questions, and enjoy the rest of your day.